Greeting students. Today we have to discuss about fluid dynamics, the introduction. The fluid dynamics is one of the most important of all areas of physics. Life would not exist without fluids and without the behavior that fluids exhibit. The air we breathe and the water we drink, and which makes up most of our body mass are fluids. Motion of air keeps us comfortable in warm room, and air provides the oxygen we need to sustain life. Most of our body fluids are water based, and proper motion of these fluids within our bodies, even down to the cellular level, is essential to get good health. Fluids in pure science. The following list, which is by no means all inclusive, provides some examples of fluid phenomena like atmospheric sciences, that is global circulation, long range weather predictions, analysis of climate change, global warming, mesoscale weather patterns, short range weather predictions, and tornado and hurricane warnings, pollution transport. In oceanology, ocean circulation patterns, cause of El Nino, effects of ocean currents on weather and climate, effects of pollution on living organisms. In geophysics, there is convex and thermally driven fluid motion in the Earth's mantle, understanding of plate tectonics, earthquakes, volcanoes. Convection in Earth's molten core, production of the magnetic field. In astrophysics, galactic structure and clustering, stellar evolution from formation by gravitational collapse to death as supernova, from which the basic elements are distributed throughout the universe, all via fluid motion. In such a cases, space-time is considered as a fluid. In biological sciences, circulatory and respiratory system in animals, cellular processes, fluid in technology. As in previous case, we do not intend this list of technologically important applications of fluid dynamics to be exhaustive, but mainly to be representative. In particular, internal combustion engines, all types of transport systems, turbojet, scramjet, rocket engines, aerospace product population systems. In waste disposal, chemical treatment, incineration, sewage transport and treatment. In pollution dispersal, in the atmospheric smog in rivers and oceans. Steam, gas and wind turbines and hydroelectric facilities for electric power generation. In pipelines, that is crude oil and natural gas transfer, irrigation facilities, office buildings and household plumbing. Fluid structure interactions. Design of all buildings, continental self-oil drilling rings, dams, bridges, etc., aircraft and launch vehicle airfarms and control systems, heating, ventilating and air conditioning systems, cooling system for high density electronic devices, digital computers from PCs to supercomputers, solar heat and geothermal heat utilization, artificial hearts, kidney dialysis machines, insulin pumps, etc. Now, definition of a fluid. What is a fluid? We are now in a position to examine the physical behavior of fluids, and by so doing, see how they differ from other forms of matter. This will lead us to a precise definition that does not suffer the deficiency alluded to earlier. That is, being unable to determine whether a substance is or not a fluid. Shear stress induced deformation. The characteristic that distinguishes a fluid from a solid is its inability to resist deformation under an applied shear stress. There is a tangential force per unit area. For example, if one were to impose a shear stress on a solid block of a steel as depicted in figure 2.2a, the block would not begin to change shape until an extreme amount of stress has been applied. But we apply a shear stress on a fluid element. For example, on water, we observe that no matter how small the stress, the fluid element deforms, as shown in figure 2.2b, where the dashed lines indicates the vertical boundaries of the fluid element before application of the shear stress. Furthermore, the stress that is applied, the more the stress applied, the more the fluid element will deform. This provides us with a characteristic saying future of liquids, gases and fluids in general, that distinguishes them from other forms of matter, and we can thus give a formal definition, that is, a fluid is any substance that deforms continuously when subject to a shear stress, no matter how small it is. These are the examples. 2.2a, that is a steel, then B is water. Then in 2.3, the behavior of things that flow. If we pour sugar, some of sugar in a table, and the second example is full of coffee. The coffee deforms continuously, but the sugar stops at a certain stage. Sugar is a solid substance and coffee is fluid. We will later need to be able to study forces acting on fluid elements, and shear stress will be very important in deriving the equation of fluid motion, and later in the calculation of drag due to flow over submerged objects and flow resistance in pipes and ducts. Since shear stress is a tangential force per unit area, we can express this for a finite area A as tau equal to F by A, F divided by A, where F is a tangential force applied over the area A. This is the average shear stress acting on a finite area A. But in the derivation and analysis of the differential equation describing fluid motion, it is often necessary to consider shear stress at a point. The natural way to define this is tau equal to limit del A approaches 0, del F divided by del A. Thank you, students. We will see you in the next class.